I always make this. This is an informal seminar, it's a lunch seminar. We don't have as much pizza in the plates will be delivered, again, as we hope, in a few minutes. And so feel free to grab pizza during the talk. But it's a real honor to have as the last speaker of this quarter, Maxime Zubkov. It's actually our first visitor that has not been local to Seattle or to University of Washington. So it's an honor to have him here present the title is Geometry and Expressivity of Neuromanifolds, where algebraic geometry meets neural networks.
So hi, everyone. My name is Max, and today I'm going to talk about my obsession for the last 2 years, with neuromanifolds, as a continuation of my graduate studies. The roadmap for today, we're going to remind ourselves quickly what are neural networks, and I will tell you how I think about them. After that, using this idea in mind, we're going to define neuromanifolds and jump into discussing algebraic neuromanifolds. In other words, like algebraic machine learning. And after that, my research is focused on two particular families. It's polynomial neural networks and rational neural networks. So I'm going to give you the overall overview, what have been done so far, and talk a little bit about my personal research. And after this, to be honest, I was finishing slides this morning. So I'm going to talk a little bit about my summer project with undergraduate students when we started looking into neuromanifolds for finite fields. And also, I'm really application minded. I'm going to show you some of the numerics and experiments, how this possibly can be applied to other fields. So for this talk, I'm going to talk only about feed-forward neural networks. When I think about them as a composition of affine maps with nonlinear coordinate-wise optimization functions. But in particular, for this talk, I'm going to take neural networks without bias, because my goal is to study rational neural networks with 1/x activation function. And when people study polynomial activation, they usually take the monomial activation function also without bias. But the same ideas that we're going to talk today have been applied or can potentially apply to other architectures, which are convolutional neural networks, recurrent neural networks, transformers, etc. So an example of neural network you can see here is just you have 3 input parameters, and you have just one output, 2 hidden layers, where each layer is of dimension 3. So after we have the neural network, then what we can do, the idea we're going to fix the architecture. We're going to fix our dimensions. And we also fix the activation function. And as soon as we fix those two parameters, those two objects, then when we train a neural network, it means we're going to change our parameters W's, which are in this case, again, they're going to be just matrices of this form. So in other words, I can consider the parameterization, because I have my neural network. It needs to live in some ambient function space. Then when I'm going to change my parameters, you can imagine that in this embedding of the parameter space into the ambient space, your neural network is going to travel on its image. And some examples of the ambient space, when we're going to take continuous activation function and study functional compact set, you will just take you will have infinite dimensional space of continuously compactly supported functions. But the beauty when you will restrict your continuous activation to polynomials, then your ambient space is actually going to shrink into a finite dimensional space, because the output of the neural network is going to be just the tuple of polynomials of bounded degrees. So in other words, the idea of the slide that we pick our parameters and we produce an element in our ambient space. And this is I really like images and visualization. So we pick our parameters and get an image, a neural network. So what is a neuromanifold? How I think about neuromanifolds? So again, we have our fixed architecture, we have our parameter map. Then I want to talk to take as big as possible our ambient space. So I'll just take any functions from RD0 to RDL. I'm not going to restrict myself to continuous and non-continuous, because I will consider rational activation functions. And then what we're going to do, the image of this parameter map, we're going to call the neuromanifold. In the literature, in machine learning literature, it's also known as a hypothesis class. So in other words, it's all possible representable functions in your ambient space exactly by your neural network. And again, like a small image, you kind of look at the embedding of the entire parameter space into your ambient space, and the image is your neuromanifold. I really like history, so I decided like kind of to jump and dive a little bit into where is like the first appearance of possible like neuromanifold, or where people were interested to study like the geometry of the image of the parameter map. And actually, the first mentioning of the kind of neuromathematics was by John Neumann in his book Computer in the Brain. And the idea, he said, there more or less that we need a new type of mathematics to describe how our brain works. And then only like after like 33 years, the Amari, in his paper, The Holistic Geometry of the Manifold of Higher Order Neurons, proposed kind of the study actually the geometry of the manifold of the neurons, which is exactly like what we're going to study today. And it took him around like 15 years, and there was an entire like research program where they connected the concept of neuromanifold, but from the perspective of information geometry. In other words, they were thinking about your function as kind of probability distribution, and they were able to define some like Riemannian metric, and they had the entire work of this kind of neuromanifold studies from that perspective. And the main idea, kind of the amazing paper, that they looked at the training dynamics of the neuromanifolds, and they connected it to singularities and how it actually affects the learning dynamic. So in some sense, it's kind of this stochastic version of the neuromanifold. But I really like algebra in geometry, so that's why we're going to jump into algebraic kind of neuromanifolds. And the first study were with RLU activation function and how it's connected to tropical geometry around 2014 by Guido and others. And then like in 2019, there was proposed the polynomial activation functions. And like the study in terms of expressivity and filling like notions of the neuromanifolds, which I will define a little bit later. But the idea is that what we can do, we can take our neural network, pick algebraic activation functions, and as soon as we do this, in particular for polynomial one, so let's take a look at this one. For polynomial, what is like the most fun polynomials? It's a monomial, yes. So I'm going to take a monomial activation function, just x to the r. And in that case, our ambient space is going to get restricted even more. So we're going to kind of project the entire, in that case, that we had like the product of polynomial rings into its symmetric parts. Because in this activation function, your neural network is actually going to output the tuple of homogeneous polynomials. And then in this case, this space is finite dimensional one. And as soon as I have a final dimensional space and you see like sim, then like we can consider this over complex numbers, take projective space, and we're going to be in the realm of algebraic geometry. And then we have the entire toolkit, which we can apply and try to study the image of this map. Because what we can do, we have in this setting like Zariski topology, and we can take the Zariski closure and we will define the neurovariety, which in this case is actually going to be a reducible one, because it's given by the polynomial, by the image of this Rn. And then for this algebraic variety, we can just ask the questions: what is the dimension? What are defining equations? And what are the degrees? What is singular locus, curvature? We can look at the fiber symmetries, Euclidean distance degree, logomology, and other like related topological invariants. So basically, the idea is now you have this kind of small, cute neural network with algebraic activation function, and you can try to do experiments and study this neural network using, because most of the methods that are now in the machine learning community, they use statistic probabilistic methods, yes. But this provides like more like algebra geometric approach when you can actually get your hands on the training dynamic and try to understand using these invariants. Okay, so I will stop here just for a second. Is there any questions? Yeah.
Do you know, or is it known in general, like how distant is the Zariski closure with the actual thing? I mean, if that thing contains like, even a very, very small open, the Zariski closure is the whole thing.
Yeah, there's a paper, Geometry for Neural Networks, and they looked at one particular architectures and they compared the Zariski closure and Euclidean closure. Okay. Yeah, so there's some work on that. Yeah. And why are we doing this? Because there's a paper, Introduction to Neuroalgebraic Geometry. It's the field as intersection between algebraic geometry and machine learning. And they proposed this dictionary where we're going to look at all previous like toolkits, like dimensions, singularities, fibers, and how this can be translated into the language of the machine learning community as for dimension, sample complexity and expressivity. For singularities, it's connected to subnetworks, implicit bias. For fibers, it's identifiability and invariance. And critical point and dynamical invariance are for optimization gradient descent. I really like examples, and I do in study math by just considering like kind of a sequence of examples in increasing difficulty. So let's start with this one, like 3 to 1. So in this case, we have square activation function. And what do we have? The output of this neural network is going to be just a single output, which is given in this setup as a sum of 2 linear form squares. So in other words, if you're going to expand this, we're going to have a quadratic form. And this quadratic form is actually, for this quadratic form, you will take the corresponding symmetric matrix. And because the symmetric matrix is going to be written as a sum of 2 rank 1 matrices, it's actually going to be rank 2. So basically the idea of this one, that this hidden layer controls what rank you're considering for your matrix in this case. And we all know how to describe matrices, 3 by 3 symmetric matrices of rank 2. We just take their determinant. And in this case, our parameter map is going to be like, we have 8 parameters, like 6 plus, 6 plus the 2. And we map this into our ambient space, which is going to be just R6, because we identify our symmetric space with R6. And here you can see a slice when I'm going to take my C1, C2, C3 equals to 1. And this is how your the slice of your neuromanifold is going to look like. But actually, if you're going to take Zariski closure, it's going to be itself. So because this is actually going to be our algebraic variety. So yeah.
So a priori, you had your ambient space to be the whole function space from the parameter R8 to R, right? But now you're saying that so where does the sim to R3 come from?
This is the space of symmetric matrices of 3 by 3 symmetric matrices. Because the idea, like, you can take an ambient space as big as you want, but you're interested to shrink as much as you can. And I'm telling you, it doesn't matter what parameters in my network I'm going to pick, I will never escape this space.
Okay, I see. I see.
Can I, like,
Yeah.
is there a reason why you don't consider bias in the transformations WI?
So like, reason is really simple. With bias makes it way more complicated. But people do consider bias right now. Yeah. But first, the idea here, in this particular case, these neural networks are interesting because I'm going to talk a little bit. This shallow networks corresponds to CP decompositions of the tensors. So that's why, like, you can do some sort of tensor decompositions by studying like under this neural networks and stuff, or learn something about these neural networks whenever you know about symmetric tensor decomposition.
What do you mean by activation function? Does something?
Oh, activation function. Yeah. For example, here I start with like x, y, z, let's say, yes, and I'm going to, when apply W1, I'm going to have the vector with linear forms, and by activation function, I'm going to do like take these linear forms and square them, and then take the linear combination. So activation function means like you just apply coordinate-wise some nonlinear activation to your vector. Yeah.
Oh, can I also ask, maybe you already show this in some later slide, but if your activation function is not a monomial, but just a polynomial, can you identify what the function space shrinking will?
Yeah.
Oh.
Yeah. Okay, so let's discuss quickly for this one some of the results in terms of dimension. So dimension is going to be 5. The degree of our polynomial, which are getting like 3, is given by this kind of rank 2 matrices. So our neuromanifold is going to be cut out only by one equation. Some geometry and identifiability. The singularities in this case are going to be given by rank 1 matrices in this case. And what is interesting that if you're going to look at the fiber of this parameter map, then there are some results. The fiber is going to be given just by permutation of your linear forms or by some kind of rescaling. So the generic dimension of the fiber is like at least 2. So you expect that this dimension of your neuromanifold is going to be 6, but it's actually 5. So it means you have some extra symmetry like hidden here. And this is actually, we're going to talk about this called like defective dimension. So that's why when you have these neural networks, you have this here set up, you have your neural manifold, you expect some dimension, and but sometimes you have some extra hidden symmetries. So that's why when you're actually going to go and compute that directly, it will not coincide. And when it's not coincide, it's called like kind of defective architecture. So here, yes, short. I'm not going to dive too deep, but the idea is like what is now is interesting is you have like this finite dimensional ambient space. You have your algebraic variety, and you can take some generic point in your ambient space. And what you're going to define, we're going to define the distance from our generic point to our variety. And you want to ask, with this kind of notion of distance, how many critical points do I have? And what people one of the most recent works is just the Euclidean distance degree of smooth complex projective varieties. They show that if you have like smooth variety and you have some restriction that you don't want it to belong to this cone, then in this case, your Euclidean distance degree is going to be given by just the earlier characteristics when you take some generic hyperplane union with your quadratic, like throw away from your algebraic variety, and you will get the actual number of the critical points. So the point kind of this slide, what I'm trying to say, that one of the work that people do, they're trying to figure out the number of the critical points, and there's really beautiful algebraic geometry involved, how it can be computed. A concrete example for symmetric matrices by Eckhart-Young theorem, we have that if you have 3 by 3 matrix of rank 2, you expect like 3 critical points for Euclidean distance metric. Okay, so before I'm going to move to the next one, any questions?
Oh,
Yeah.
Can I ask a question? So, is there any like benefit of say, projectivizing or compactifying both the source and the target? For example, like we've been talking about like maps from Rn to some symmetric, however variety. Can we like maybe projectivize both sides, and does that like get us interesting? Or can we like add some like points at infinity, and then does that maybe just like is that a valid question to be thinking about?
Yeah, that's sometimes thing because the idea is like if you want to apply these neural networks, yes, people use different notion of metrics kind of when they train on their data. And so what is interesting, but most of the time people like focus on a parameter space. But what is interesting, like depending on the choice of your metric, how like the training dynamic is happening actually like in the ambient space. So there is some notion of this kind of natural gradient descent where people trying to incorporate the like curvature and the geometry of the kind of the neuromanifold to amplify kind of the training, like because you have this one singularity. So during the training process, the idea is overall you want to avoid the singularities. So that's why like there is some work on that, yeah. Okay, so next section is polynomial neural networks. So here we're going to talk about when the dimension is failing. So basically the idea is like we have this expected dimension, which comes basically from parameter count minus the the obvious symmetries that we might have in our fiber. And when the expected dimension is not met, then we're going to define the defect, which is the difference between our expected dimension and the actual dimension. In this case, when we have the neurovarieties, which are where like dimension is defective, we're going to call them defective. And there was like the entire small like research program for the last like 6 years, where people was trying to understand for the generic architectures with monomial activation functions, which are varieties are defective and which are not.
Question.
Yeah.
So this D vector is the number of neurons in each layer.
Which one? D?
Yeah.
Yeah.
I think it was using D1 to DL. I think the notation has changed now from D0 to DL now.
Yeah, it's from D0. Yeah.
I think the previous slides were D1 to DL. From the first slide.
Probably there was some, up to some typos. Module some typos, yeah. So, okay.
If I have an open inside the space of parameters where I know that the symmetries are only the standard one, do I get the equality?
Yeah.
Okay.
So the more or less the idea is like, at least for I observed that whenever you start talking generically, everything works out nicely. But the question is, whenever I want like kind of to actually go and dive deeper how the image looks like, then it's when they start getting way more complicated.
I'm a little confused with the notation. You're using VDR to call the space and the number?
Oh, yeah, there's a typo.
Oh, typo, yeah, it's expected dimension, yeah.
No, but the difference you're defining to be.
Oh, yeah.
Oh, it's probably, okay, I was like copying from this like defect.
Okay.
Yeah, defect,
Yeah.
Yeah, because I use like different this kind of comment and overleaf, so they probably just didn't cut it. Yeah. Okay, so the beauty is that now we have a lot of results from classical algebraic geometry, and when we have this setup of polynomial like algebraic neural networks, we can just go and translate those results, trying to understand our architectures. So we have Alexander Hiroshevitz's theorem, which tells us that when we have this architecture, so in other words, you have your homogeneous forms written as a sum of m linear forms to the power of r. And you want to figure out in this case, which are varieties are going to be defective or not. And you have actually like real nice classification. Again, like for the square activation, as we discussed before, all of them actually are going to be defective. And you have only 4 special cases for activation degree when it's bigger than 2. A week ago, there was a published paper on overleaf, where actually the Alexander Hiroshevitz's theorem for neurovarieties. So this question was already like officially disclosed. So now people figure out with some extra conditions how big do you need to make your hidden layers and how big you need to make your activations. Because what they do, they can each separate activation for each of the layer for a monomial. Then they computed actually the dimension of this neurovariety. So far we discussed only like one invariant, which is like dimensions. So then what's next? Why do we care? So here, one of my work which I do right now, we're trying to figure out the defining equations for shallow PNNs. So in other words, we consider the architecture NMK, where the hidden dimension is no bigger than your input dimension. And this is equivalent that you have K homogeneous forms. And what we do, generically understanding the point in your neuromanifold is equivalent to simultaneous diagonalization of K symmetric tensors. And overall, we know that we have this geometric invariant theory that you can go and we have the procedure, the algorithms how to find those equations, but usually it's really hard. But there is some nice properties and some really short description. At least what we have done so far, we show this for K equals to 2. We kind of compress all these equations in one real nice property, which is equivalent, like overall idea is if you're going to give me 2 symmetric tensors, I'm going to produce another tensor. And we're going to say that this 2 matrix tensors belongs, like this point which you gave me belongs to the neuromanifold if my new produced tensor is going to be symmetric. And this is kind of equivalent to the idea that if you have a matrix, it's going to be diagonalizable if it's a symmetric one, which is like really nice. Then defective architectures. So the problem with like kind of this result that most of the time we need to make our activation functions too high, or we need to make our dimensions too high. And what?
Is this a home?
Yeah.
So this is like a complete classification.
Yeah.
Of what the defects.
Yeah, the paper is really beautiful. Like they literally kind of went in and described geometry completely. They explain and motivated everything, like why dimension drops. Because they look at the actual Jacobian of the parameter map and they kind of use some block diagonalization and they analyze when each individual block is going to drop rank. That's more or less the idea. Yeah, so what is interesting, like to study actual defective architectures, to explore and look at those hidden symmetries. The big picture, which, let's say will take maybe forever, is the question is, can we use this algebraic neuromanifolds to approximate analytic ones? So what I mean, what do we have? We're going to take continuous and polynomial activation function. Can we construct a sequence of this algebraic neuromanifolds which will approximate it? And which properties of this neuromanifold geometric properties will be preserved? or how understanding something about this neuromanifold can help us understanding about actual architectures that people use in practice, because they use RLU activation function, they use hyperbolic tangent. So this is like the big overall picture. Another thing is like universal notion of the neuromanifolds, because we have the ones from information geometry and we have these algebraic ones, and can we unify them and put under one umbrella? Can we use something that people already studied for information for like geometry notion of the neuromanifold to help understand like neuroalgebraic ones in opposite? And finally, like applications. And in my talk, I'm going to show in the end like two possible applications. Is just how we can use rational neural networks to learn some singularities, and how by looking at the neural networks over fine fields, you can get a better understanding of quantized networks. And by quantized networks, I mean that you will take your parameters be just plus minus one or 0 plus minus one, or like some finite set of numbers. First, let's talk about rational activation functions. And the question is like why we want to move beyond polynomials. So first, like we have universal approximation theorem, which tells that our neural network is not going to be a universal approximator if our continuous function is polynomial. So it's the first thing. Then,
but if you're allowed to change the choose any polynomial for the activation function.
yeah, if you,
then the approximation theorem still holds.
maybe. Yes.
Okay.
Yeah.
I would expect, but yeah.
Yeah.
You need an arbitrary degree, right?
Arbitrary degree.
Arbitrary, yeah. That will hold. Then another thing is it's basically unstable during the training, and we have like kind of gradient explosion, and we're all like in class. Okay, I didn't do like approximation theory, but rational approximation behaves very nicely than like polynomial approximation. And using these ideas, especially this one, they try to apply and compare rational activation functions with RLU ones. And the idea more or less that rational activation function behaves more nicely when you allow to train your activation function themselves. And in that case, you will require way less parameters to train and obtain the same efficiency than with RLU networks. To make them universal approximators, then people start considering like the activation units. The idea is that you consider the rational activation function when you require that your denominator will stay away from 0 because you don't want any explosions. But part of my work, I said like, okay, so let's actually allow those explosions. Let's kind of have this continuous activation function. And in that case, I will show later that you can actually try to learn some singularities, which comes like from PDEs. And one of the examples, like people learn the Green's function. Finally, using this for the approximation, when I'm going to talk about rational activation function, you can connect it directly to some already known algebraic varieties, which are called Taylor varieties. Did I miss some slide? Okay, yeah, there's one miss. Oh, instead of missing slide, let me then show it to you. I really like visualization. Second. So here you can see I take the same architecture and I change two different activation functions. I have rational one of this form, RLU, and hyperbolic tangent. And you can see how rational activation function is more flexible and more kind of proponent of learning some periodicity and stuff. RLU got stuck and hyperbolic tangent learned something, but then it, yeah. Okay, now is part of my work. So now what we're going to do, due to all of those limitations, I want to jump from polynomial activation one to rational activation. And we discovered the first problem. If you will take the space of all rational functions, it's an infinite dimensional space. So how we can deal with it? There was two general approaches which I was thinking about. The first one is like really trivial. You just fix the architecture, and when you're going to fix the architecture, the degrees of your numerators and denominators are going to be bounded. So that means you can just take those coefficients, like put them inside the vector, and since you have kind of rescaling, this vector will land in the product of projective space. So that's why kind of the first approach which I took. There's one paper, and they give the paper, you have the rational function, and you can approximate it with order m Taylor polynomials. And what you're going to do, you're going to look at the coefficients of your Taylor polynomials. So you also have finite dimensional space. And those coefficients will cut out some variety, which they call Taylor variety. And in that paper, it's like called like Taylor variety written by Bern. They actually give complete classification of these varieties. But one problem is that if in this notion you can just jump directly and look and study like the parameters of the network directly affect this coefficient, in order like to use this approach, you need to go like through some lengths because there's some restrictions. So that's why I decided not to take this approach, and we took this one.
And wait, is the activation function fixed, like 1/x, or?
Yeah.
Or
So in this so far case, it's just the idea that you take any rational activation function, but I'm going to fix it. Because people first were studying like linear neural networks with linear activation function. And I was thinking like, okay, which activation function can we study? 1/x. And one of the nice thing that if you will take just 1/x and you will take shallow architecture, then you studying neuromorphic function with linear poles. And there's a lot of literature on this that people have already studied. And first of the like just trivial result that for polynomials, we can describe this ambient space because you have just a polynomial. But when you have like some rational activation function and you apply it like iteratively, what is going to be the dimension kind of this space? What are these degrees? So first thing that we did, we gave a recursive formula for the output, but using this recursive formula, we can actually compute the dimension of our numerators and denominator. Another awesome thing that all denominators are going to be the same. So in some sense, we have a smaller space. Instead of taking like all possible, you just need to take like one. And and this is like a recursive formula over here. So the idea is like first we got the dimension of our ambient space. And then as soon as we have the dimension, all of the numerators and denominator, because again, like you have 1/x, are going to be homogeneous polynomials. So that's why we take this parameter map this parameter map where you map to all coefficients of your numerators and you have the L of them and to the coefficients of your denominator. And the total number of parameter is equal to this, but the dimension of the ambient space is way bigger. So that's why if we want to kind of continue studying like defective architectures or like filling and non-filling, I will define what does filling mean. Then we need to figure out first when you even will have enough parameter to possibly cover the entire space. So by taking the Zariski closure,
In that very nice training video that you showed us, you choose a continuous functions as a rational, like one more 1 plus s.
Yeah.
Have you tried with 1/x?
Yeah, I will show it.
Okay.
Yeah. So first we again neurovariety is the same. We take the Zariski closure of neuromanifold in the space. And we're going to call the neurovarieties filling if it's going to be equal to the entire ambient space. So in other words, you have your rational activation. So rational neural networks is 1/x activation function. You have your neuromanifold, which is image. And if you will take the Zariski closure, if it's entire space, we call it filling. And the entire architecture we're also going to call filling.
So what are the filling polynomial neural manifolds?
Yeah, I'm going to show it.
Okay.
Yeah. So then we did the following. So the problem is, again, like you need to pick some specific problems, at least like try to understand. So we picked just shallow architectures and deep binary architectures. And we did the following, that membership problem is just, if you're going to give me some element in the ambient space, does it belong to a neuromanifold? And we were asking like a specific one. Can you find the weights which will map to this element? Then filling architectures characterization, we discuss which one architectures are filling or not. And model description. Can we get some kind of geometric intuition? What is our like neurovariety even is? Or what algebraic geometry object do we need to understand our variety better? A second example of this talk is architecture 321, the same one, but with 1/x activation function. And here, let's kind of do it slowly, this computation. I apply my W1, going to get two linear forms. apply my activation function. So I'm going to inverse them and take the linear sum. And then I'm going to obtain this rational function, where on the top I have my linear polynomial, and on the bottom I have my quadratic form. Okay. So in other words, membership problem. Now we're going to play a game. We're going to imagine that we in like multivariable calculus, point 2, which is like not that. We're doing kind of partial fractions for multivariable rational functions. I'm going to give a partial fraction, and I will tell you, can you write this partial fraction as a sum of these two inverses of the linear forms? And if you're a good student, you will like just play around a little bit with this example and figure out that what you need to do, you need to take the coefficients of your numerator, put this as a row, as a column vector, take the symmetric matrix of this polynomial, sorry, this quadratic form. Okay, so just divide this, either this one or you can take like 1/2. So it's up to coefficients. And when you're going to take all 3x3 minors of this matrix, when they're going to vanish, that means you can write this as a sum of inverses of the linear forms. So that's why our first description of the architecture, you take architecture N to M, and now we're playing this kind of, I don't know, multivariable version of multivariable version. When you take M fractions of the form linear over quadratic, and you ask when like this rational function is going to belong to a neuromanifold. So you take the coefficients of your numerators, create your columns, take the coefficients of your quadratic form, create this big matrix, and your neurovariety is going to be cut out by 3x3 minors of this big matrix. And we computed the dimension and we got all of the equations. So here we do N to M. And the question is then, okay, but what if we have NMK? And let's not try to describe, give defining equation, but let's try to describe kind of the process, how you're even going to check if the given tuple of rational functions P over Q is going to belong to our neuromanifold. And first you need to observe that your denominator needs to be written as a product of linear forms. And this is our exactly like our Chow variety. And what is the beauty of it? As soon as like you have the algorithm, you first check if Q is written as a product of the linear forms. If it does, then you need to find this actual like, kind of this like linear forms kind of decompose. And when you find them, you plug in them into your numerators and solve the linear system. So in other words, yeah, now we can play this game again when we have classical results of algebraic geometry, try to bring them into this architecture and try to understand this better. And one of the kind of hint was that the equations of neurovarieties may be given by the Brill's equations. And actually, yes, this is your Brill's equations that we have over here. And I'm going to jump to architecture 331. So in this case, what do we have? We have the output quadratic over cubic. And we thought, okay, maybe we need to make some tensor and stuff, but unfortunately, the things are not work out that nicely. So first, what we were able as a partial results, I'm giving just examples, we were able to describe some equations for the generic architecture NMK. But unfortunately, those equations are not enough. For this particular problem, we can see that these equations some equations are given as a 4x4 minus of this matrix, and they give us the dimension of the neuromanifold is 13. But we know that the true dimension is 10. But then we're like, okay, we have here like these conditions. Maybe we need to add Brill's equations to these equations. We add Brill's equations and dimensions drops to 12. Still not enough. And then we did some voodoo, which is like what's called like multi-graded implementization. And we actually obtained 185 homogeneous polynomials of degree 4. And the question is like, how can we get these equations kind of directly? What we can do? Let's check on time. How much time do I have?
15, no less than 15.
Okay, yeah.
Can I ask which one you're referring to as Brill's equations?
It's if you give me the form and you ask if this form is written as a product of the linear forms, Brill's equations are kind of responsible for that in some sense. Yeah. The idea is the following, that if you have a shallow architecture of NMK, then let's say you're going to give me rational functions P over Q. Then I'm telling you, to figure out if this rational function belongs to your neuromanifold, what do you need to do? You need to make your life a little bit more complicated by cooking up this bigger polynomial, this new introduced variables set. And what you can observe, if this is going to split as a product of linear form, then in these linear forms, you can recover your coefficient stack. So that means to figure out if the point belongs to the neuromanifold, we need to check if there exists like these polynomials such that it factors into product of the linear forms. And as one concrete example is here, you have architecture 331. So I'm saying that you give me a rational function P over Q. I'm going to create this polynomial. And what I want to do, I want to apply the Brill's equations to figure out when it splits into product of the linear forms. In those equations, we have one problem. Like Brill's equations are really, they're not our friends. For this example, we already have 875 of them. So that means it's just a nightmare. But what we can do, we have there like 20 variables. And in those 20 variables, there are 4 variables that we don't care about. It's just U1, U2, U3, U4. So it's kind of the conjecture, but to obtain this 185, we didn't do this computation. I didn't even try to do it because the probably algorithm will not finish. But to obtain this 885 equations, you just need to eliminate these parameters over here, like U1, U2, U3. So you kind of need to, use Macaulay too, but we didn't try. So it's probably one project to do. Filling architectures. Okay, here I will do quickly. For NMK, for the shallow one, only one-dimensional input or two-dimensional inputs. One-dimensional is not interesting one. So the only filling architectures of this form, NMK. So in this case, neurovariety is going to be the entire thing, but neuromanifold is actually going to be constructible in this case. But open Zariski is really nice. And open Zariski is exactly like a simultaneous diagonalization of the tensors. For the binary architecture, when you have 2, 2, 2, 2 DL, only possible candidates for the filling architecture 1, 2, and 3. So you have single output, 2 outputs, and 3 outputs. And only the single output is going to be the filling. And these ones are like not. And the idea, these are not filling because they need to share the common factors, and that's some kind of discriminant restriction. And the dimension conjecture in hypersurfaces. What is interesting that if we do some computations, then the only trivial symmetries are the same. It's going to be rescaling and permutation. And based on our computations, we think we actually don't have defective dimensions, at least. No, we didn't find any. So that's why we conjecture this is our actual dimension of the neuromanifold. But what is super interesting that I mentioned about Euclidean distance degree or studying those invariants, some of the architectures are actually hypersurfaces. So in this case, we have architecture 2, 3, 2, 1. The ambient space is 11-dimensional one, but the neuromanifold is 10-dimensional one. So that means this neuromanifold is given only by one equation. We computed for 10 hours trying to find these equations and didn't find it. But the idea of more or less, by having just one equation, you can go and try to answer about like Euclidean distance degree or get some better understanding of the behavior of this neural network, because the image is really nice. Image is literally like a hypersurface.
How did you verify that the degree must be almost 5?
There's
at least 5.
There's this voodoo technique, which apparently using some Grosvenor basis with linear algebra. Multiplicative implicitization package. And what does it allow you? Run an algorithm like, okay, what are the possible equations of degree 2? It gives you the list. Degree 3 gives you the list. So we run until degree 4, but degree 5 never ended. So yeah.
For the non-filling cases, you have examples where the codimension is greater than or equal to 2. Like
Yeah,
it's
yeah.
not a hypersurface.
Yeah. So here from some of the examples. It's in terms of dimension computation. So here, for example, ambient dimension is 15, 14, actual dimension. No, sorry. This dimension of the neuromanifold. Okay, in this case, I've showed the examples when dimensions agrees. Okay, this one be dimension. So you have 14 and 15, but you have 17 and 23. So this one also But overall, you can see the difference between ambient dimension and dimension neuromanifold. It's pretty drastic. Okay, so let's see. I have 10 minutes. So let me give you 2 slides, a short summary of summer project. So the idea was approximately the following. We took the shallow architectures and we consider them when your weights are going to be, we're going to work over fine fields. And the kind of one of the motivation is, if you're familiar with well conjectures and stuff, then we were like wondering like, oh, can we like kind of count the points over the fine fields and try kind of to learn some motivic structure of our neuromanifold and neurovarieties. And another like possible application is the quantization of low precision, because when you could, there's like, I feel like neural network transformer, Microsoft one, it's called like 1.56 bit transformer, where they consider like ternary weights, plus minus 1 and 0, and they try to train it and compare its result to actual transformers, and actually not bad. So that's why it's gives pretty nice output. So kind of my motivation was like, oh, maybe we can understand something better about kind of this quantized neural networks if we will understand this one over here. We also submitted this to ICLR, got some responses, which is actually not bad. I thought that we're going to get like complete rejection, but we got actually like 4.5. We got into top 30 percentile. And one of the nice feedback was like, oh, what if we're going to look into like not over fine fields, but over function fields or something like that. And people give really good suggestions how this can be like applied. So what we did, we computed the, we defined the expressivity, because what is the beauty of this is your function between 2 finite fields is like, it's a discrete space, yes? You have like finite number of elements. So that's why we can describe like really nice notion of the expressivity, which is kind of just count points, really simple. Then we compare this with the complex counterparts, because for some concrete architecture in cases, we can actually compute local like zeta function, and we can just try to look and like compare it with this kind of complex analogues. But basically, like we did one of the suggestions we like talk about this, but didn't put this into paper because again, like it was like summer project, and yeah, and we compute explicit cardinality. So what we did, we repeated the result for quadratic activation function over characteristic node 2, and everything just translates perfectly, ideally. Then we described the generic monomial degrees for architectures N to K. So we counted the actual number of points in the neuromanifold. And we also look at the architectures when the activation function and characteristic of our field have both divisible by P. And in this case, architectures are pretty simple. They just kind of boils down to this kind of previous cases. And what is like the first interesting result, that if you take architecture 222 over complex numbers, it's equivalent to understanding the simultaneous diagonalization of 2 symmetric matrices. And overall, this is going to be Zariski dense. So it means like this architecture, when you take Zariski closure, you will get the entire space. But over finite fields, you're actually going to have a half of the elements. So what we did, we computed this for this architecture neuromanifold for the primes 2, 3, 5, 7, 11, take the ratio with total number of the points in space. And again, like when I talk about the space, I'm thinking about my output as a polynomial, because we have this problem that the kind of map from polynomials into functions is not going to be injective. So that's why we first just dealt with polynomials. Then we observed that the ratio of the neuromanifold to the ambient space goes to 1/2. So it means like this, in this case, the neuromanifold in some sense filling in the half of the ambient space and cannot do better. And big takeaway just overall for this neuromanifolds over fine fields is this kind of possible connection between a neural network theory, tensor diagonalization problems, because not every symmetric tensor of fine field can be written as given a CPD decomposition. So it's like, I didn't know about that. And probably some arithmetic geometry. Yeah, but basically trying kind of disconnect these 3 fields, like neural networks, fine fields, and blah, blah. Okay, numerics for the last 5 minutes. Okay, so here I'm going to take 10 by 10 by 10 symmetric tensor of rank 5. And what are we going to try to do? We will try to use shallow neural network. When you have this tensor, guess what is going to be its rank without knowing it, let's say. And what you can do, you can train your network for rank 1, rank 2, rank 3, 4, etc. And when I say this, it means you change your hidden dimension because you have architecture n, m1. So you just change your m from 1 to 10. And what we do, I train this neural network, let's say 100 random initialization points, and see like for 10,000 steps, I'll say. And see and record it is going to be my final loss. So in this case, you can see of rank 1 training. We train 100 times, and most of the time we're going to get stuck around the 3.5 final loss. Yeah.
What's the activation function?
X to the 4. So it's order 4 tensor. Yeah. And but the idea here, this is example of rank 5 and rank 6. Along this axis, I record the results of my final loss along y-axis. So you can see this drop between 4 and 6. And this drop kind of indicates what is a possible rank of your tensor. And here's the idea is more or less that because for these architectures, when you train them, the final weights kind of your linear forms itself, which are responsible in your tensor decomposition. So that means your final weights are really interpretable. So by training this neural network, and if your loss is going to drop into 0, you can learn actually about your algebraic object, something new. So in this case, we were trying to learn the rank.
There's not much time. Maybe
Okay, yeah, okay.
Just because there's a seminar that comes in right after this. So
Okay, and the last one, just one sentence. You gave me this neuromorphic function. I sampled this function on a lattice. I used 1/x activation function, and I reconstructed the functions. And I'm done. This is the conference that we organized at BBC, and this is the paper of rational activation functions. Thank you. Yeah.
we'll take their time. One question, but Maxine or Max will be around the rest of the day. So.